this session essentially will talk about the role of open source in AI, but I know it feels a little bit odd. It is like saying, am I audible?
Yes.
It is basically like saying the role of oxygen for human beings, right? So, well understood, but I'll still go into it. Today what I'll cover is the current timeline. Timeline is the word I'm using because we all should feel quite lucky to be in this timeline if you believe in the parallel universe theory, where all of this is happening. Then we'll talk about what role open source is playing, and after that we'll also talk about the synergies between open and closed technologies. So often you will see a fight going in like open versus closed technologies, open LLM versus closed LLMs, but there are a lot of use cases where you combine this tech together to achieve something. In fact, if you look at the actual deployment patterns out there in the world, or the applications that you use on day-to-day basis, it's always like a combination somewhere. And with deployment pattern in mind, I'll also cover some of the deployment patterns, especially as it relates to AI applications. And then I'll leave you with some thoughts around how the future is going in a way that is quite deceiving, because the examples that I'm giving for like where the future is going already has happened in present. So, but take that as a guidance of what comes after this. Okay, so you already know about me, so I don't need to spend time there. So let's talk about the current timeline. Neural networks itself, or machine learning as a field in general, AI, these are not new techniques. They have been done for like so long. Like for example, bag of words. If you put out the NLP techniques where transformer is on the cutting edge side of it, and it started on bag of words side of things. And then n-gram, which is still used in many applications, got invented in just 1980s. And those of you who are familiar with Emacs, there is a psychiatrist that sits inside Emacs that is essentially influenced by Eliza, which was like the first chatbot that got created. And from there's like a bunch of innovations that happened on RNN and LSTM, and that got us to transformers. And there are like many more technologies that got invented post this as well. And as this was happening, when Google introduced transformer, this was essentially this was more of an optimized architecture more than anything, because it allowed for compression at like a large scale without wasting too much of compute. You can go into transformer paper, there's like a lot of details on how it works and why attention is important. But if you just distill it down, right, it's an optimized architecture. If you not do it this way, the amount of compute that is required to achieve the same results will be very, very high. So, and on those timelines, as the transformer got invented, a bunch of models that came out all the way from 2018 to 2023, some from Google, some from OpenAI, some from NVIDIA, some from others as well. And this essentially laid out the foundation. The reason why I'm opening with this here is the whole open source thing, right? So open source is not just about software which is open source, which die-hard fans like Richard Stallman would say. I would say look at open source more in the nature of open research. So transformer, we could have invented it, used it at Google, and never told the world about it, right? That wouldn't be called open, and all the innovation would be with us. But transformer itself was put out in a paper so that folks can then look at it, how it was implemented, and then they can create an implementation out of it. So that is what we have to draw from OpenAI. In fact, most of the research that still happens, barring some of the models mentioned here, have detailed research papers available. Lately, for large commercial models, we have moved to an approach where we publish technical reports more than papers. but it's still useful to see how the whole thing is evolving. One of the important aspect to understand what is happening in this era is in the classical landscape, and which I will say like the pre-transformer era, we used to have an approach where one architecture per community, and here community I am spacing is with the types of use cases that the community is focused on. So if you are working on computer vision, then convolutional neural networks would be all the rage, and they would solve the problem in certain ways which are applicable to the problems they have at hand, right? Because they have like a lot of number of pixels to process. Each pixel has like multiple channels, right? So how do I do it efficiently? And natural language processing for things like understanding where the grammar lies, understanding the sentiments. RNNs and LSTMs were the popular technologies. They were actually, I'll say. And for speech, similarly, we have like deep belief nets for translation sequence to sequence. And for reinforcement learning, there is like a separate set of tech. And if you look at this, all of these fields are quite vibrant still. This is not to say these are not important anymore, but just to highlight a fact that they had like a different architecture for everything. And with transformer, what has happened is it is just one community at a time. So no matter what work you have, it can be solved with transformer. So whether it is computer vision, natural language, reinforcement learning, speech, translation, and even graph science. By the way, it is still not a full list. So you have transformers, which will do time series prediction. You have transformers, which will do self-driving car, and in fact generate data for self-driving as well, good synthetic test data generation. And you have transformers, and there are early science to it. You will see how it goes, and you would have seen a lot of Google papers around it, which are doing excellent in robotics, like especially teaching them the action, the world model, and how to basically act on top of it. The good thing about this approach is we can just, if we are a researcher, we can master like this, and then we get to play around all the fields. But as a developer, it doesn't matter anyway because we are just working on even higher surface. But the good thing is the community is essentially behind it. A lot of people you would see say things like, hey, it is probably transformer is reaching a point where it may not be scaled enough. But the case in point is the scaling laws says even now that you can increase compute further, compute and data, and you can get even more properties out of it. So with that, let's look at the role of open source here. The viewpoint that I'm bringing here is from the builder standpoint, like somebody who is building solutions on top of the technologies that we are talking about, not necessarily in consumer. So you wouldn't see this as like an exhaustive startup list who are operating in different spaces. These are just some of the open source projects that I have selected, which I feel is like very useful, and some even you would have heard of it. So for example, Gemma, which is a recently released foundation model from Google, which performs really well compared to Llama 2 and Mistral 7 billion parameter model. Or something like Llama. Llama itself we can't discount because it has started the whole movement behind creating these open weights or open source models, which are small, nimble, fine-tuned for a specific task. But it is not just about the models, right? It is also about some of the libraries that exist out there. So for example, if you look at transformers, if you know nothing about transformer and you want to play with a different type of models that keeps coming out, the folks at Hugging Face are working at like rapid pace to get those implementations inside that library. Same goes for diffusers as well, which is not a transformers model. It is basically an image generation not even image generation, anything related to diffusion. They have got those papers implemented there. So for example, if you're working with image generation models like stability AI and all, you'll find it in diffusers. VLLM is like a popular inferencing system. If you have a model, how do you inference it? So there are like many different things here. Let me ask you a question now to see if you're aware of some of these things. What is on the left side with an elephant sitting on llama? Do we know what that is? So that is also a model fine-tuned on llama called OpenHathi, created by one of our customers, Servo, who have fine-tuned it for Hindi language tasks. And the unique thing that they have done is they have interspersed Hindi with English. They are working on more languages as well to basically reflect the pattern of how we speak. So we often mix these two languages. And they have built out a separate tokenizer as well, which reduces the number of tokens used when we are using Indian languages with transformers. This was done before Gemma. If you use Gemma now, that already has you covered on the token side. It has a very large vocab size. Vocab size is essentially the number of words it can convert to tokens. And it may not be words, it could be other things as well. And there are like bunch of other things which are super important as you're building applications. So for example, you must have heard of LangChain, right? This is a way to basically compose different LLM calls. But you might not have heard of DSPy. Not sure if you have heard of it. That takes the approach of what LangChain and Llama Index used to do to a much more structural way. It came from Stanford NLP department, and that allows you to basically optimize these LLM calls even further. They actually compile it and they keep even prompt generation quite that. And like I can talk like full day on what all is present here. What I would recommend is to go look up these projects when you have time, and they all present like a significant step change in what we are able to do with machine learning. For example, Bits and Bytes allows you to load these large models on consumer hardware. Llama C++ allows you to run these LLMs on just CPUs, not even GPU, right? A tool from Google called Learning Interpretability Tool allows you to see why an LLM is returning a certain result. So it allows you to explore and understand different safety related issues and also improve the quality of the output. Similarly, systems like PyTorch, you already know, there is JAX, which allows you to build out these models quite quickly. And Fast API. A lot of startups use it to basically run their applications, right? So it becomes like a front end for your application to actually be used, right? So let's talk about where we start, right? So in open source, when you're working with open source tech, we always start at the foundation model, right? And right now the state of art is, and it keeps on changing. Tomorrow somebody will come and this thing may change. But as of now, Gemma, which is available in two sizes, 2 billion and 7 billion parameter size, is the state of the art. And the reason why I'm saying state of the art is, this is the benchmark numbers. All the highlighted ones are the best in whatever benchmark we are saying. And you will see Gemma 7 billion parameter model is actually doing best in most of these benchmarks. So if you are coming from these existing models, you can give Gemma a shot. The other thing is, this is the one of the only models out there that gives you portability across many different frameworks. So for example, if you use say Llama, then you would have to use GPUs to fine tune it, to serve it. Of course, llama.cpp is there, but for most part, high performance serving will always be limited to that. Whereas in this case, this is supported across many different frameworks. So the framework that Google created, JAX, PyTorch, and even TensorFlow through Keras 3.0. And it is optimized to run across various hardware. So whether it is GPUs or even Google Cloud TPUs, you can run it. It is important to be hardware agnostic here as well, because this will give you more options as you think about it. So Google's TPU is more energy efficient, and the compute that you get out of it is often, I would put it simply, like more bang for the buck. So having a model at your hand which is like quite powerful and which is not hard linked to GPUs alone, give you a lot of flexibility in terms of when you're building out larger solutions and thinking of what it will cost for you to run it, and then define a pricing strategy on top of it. This is like a good advantage. And the other thing is, if you are already familiar with tools like I was talking about Hugging Face, like Hugging Face Transformers is there, TensorRT LLM is there for serving. This model can be quickly loaded with these tools. Again, the question might come in like, hey, why you need to support this many tools, right? Why is Hugging Face mentioned, but TensorRT LLM also mentioned? And if you dig deep, all of these systems are solving one or the other problem. So for example, Hugging Face gets you started very quickly, but to do more efficient utilization of the hardware, let's say you have decided to take Gemma and deploy it on L4 GPU, which has like a 24 GB memory. It will consume roughly all the memory, like around 20-ish memory, 14, more than 14 if you load it in FP16 format. But then that GPU also has additional data type called FP8. It reduces the precision, but it keeps the model quality same. Now that is only supported so far inside TensorRT LLM, right? So it will allow you to do more efficient inferencing with TensorRT. So I'm not saying use this versus that. The beauty of selecting this kind of framework is you are essentially in whatever journey you are in your startup. You can basically make certain kinds of trade-off without thinking of, hey, I have to rewrite the code again. So let's talk about how synergy between open source and proprietary technologies gets established. If you look at any architecture, any application architecture that is built on top of LLMs, they are not like the chat interface that you have typically seen, that the consumers see. They have a question to ask, and they basically get the answer out. It doesn't work all the way, because it may not have all the context, it may not have all the other information that is required. So what ends up happening is, again, this is a little bit old, there are more boxes attached here, but we ignore all that. It still fairly covers the general pathway that most production applications using AI actually take. So a user asks for a prompt, and then the prompt itself goes to a model, and that is where I mean open versus closed. Model shouldn't be just open source. You should also look at what the state of art is. For example, later in the talk, I'll talk about Gemini 1.5, right, which is a closed model, but then it brings some of the capabilities that are not found elsewhere, right? So you would want to integrate into your application. And then you may want to do multiple calls with the model. So one call may not be sufficient, so you would end up creating a chain. And you'd provide it with a memory so that a user coming in tomorrow, you are able to continue that session with them rather than just thinking of afresh. And you have agents and tools. So let's cover some of these things one by one. So for example, chains. So this is basically, you spoke to a model, you got a response back, you took the response, feed back to the model again, and you do this again and again because you are essentially breaking the problem into many subtasks. Agents become a lot more important because they can interact the world with external tools and get information from them. This is important to understand in the context of, say, how even humans work. I can give you some calculation myself. If you say, hey, what is 8 into 8, I'll give you 64. But if you come to me and say like 998 into 8, I'll have to think a little bit because I wouldn't know the answer. Some would, but I wouldn't, right? But if you hand me a calculator then I can get that answer for you very quickly. And the same concept goes to the LLM as well. Instead of relying on these models to do math, you give them a calculator and a way to call that calculator, which is typically implemented in function calling interface that you would have seen that many of our models support and others also do. And that allows the system to become a lot more powerful. The agent system is still important here because it runs the tool, it gets the output, it can make another call to another LLM and say, hey, validate this output. If this is good, then I will proceed to the next step. If it is not good, then agent will make another LLM call and say, hey, this is the error I received, go correct it, right? Something like this you would see in a test environment as well, which Keploy would know a lot more about than me. Other than that, few things are important like prompt templates. A lot of these models are fine-tuned with a specific template, and if you don't know the template, you'll be wondering why am I not getting the right answer. Of course, these things are now abstracted away. Many of these libraries would actually ask you just for like put the response, and then they will internally formulate it in. You would have seen like human GPT. That is how most of the models are fine-tuned. So you could, those are also important. Beyond this, you would have seen a Google paper on tree of thought and chain of thought. And what this actually does is it essentially increases the search space for an LLM to do. So instead of just taking one shot and answer, what it can do is it has the ability to basically branch through multiple responses and then take that path, and if it fails, ability to backtrack it and get the results out. And this alone, and not fine-tuning or anything like that, showed models performance improvement by in the range of 70 to 80%. It's not a small number. And what this tells you is, when you're building applications, implementing this kind of search strategy becomes quite important. So all of this, right? So what I said, I have shown you this architecture. I've shown you ki, hey, model can be closed here, but these are other things that you have to do to make sure the system works really well. You are able to use the LLM to the potential. And that is where open source actually comes in. So to build out chains, you can use projects like DSPy, LangChain, and Llama Index. To build out agents, you can use projects like AutoGen, where the project allows you to basically build out 2 or 3 agent system. One agent would be like the task creator, another agent will be like task validator, the third agent will be like task deployer, right? And it gives you the ability for users also to come in. So when it is not able to resolve a particular task, users can come in and then help it resolve it. And then advanced prompting can be done by DSPy, and tools can be done by, say, something like Gorilla, which builds out a function call specific LLM, which is doing very, very well. So these are open source enablers for something that, let's say you're working with Gemini Pro. You can use all of this with Gemini Pro, which is like a closed LLM, and get more out of Gemini Pro than if you would have just used Gemini directly, right? And this is essentially my point, that you have to look at the ecosystem, how the state of art is evolving, and essentially make use of it in such a way that you get best bang for the buck. So with that in mind, let's think about some of the deployment patterns. So do evaluation of a fine-tuned model with a bigger model like Gemini Ultra. This you would have seen in many, many different places where they would build out their own, say for a particular task. Let's say you are in a financial domain, you are working on answering financial question and answer, so you took out Gemma model and you essentially trained it on the tasks that you have, like questions that people ask from financial standpoint. Hey, how is the stock market doing? What was the trend? What was the low, high, and things like that. Okay. So basically, then you can essentially use a larger model to test out that model, how the response has been. The other thing is you basically filter, reduce, or route your queries and response before sending it to a larger model. So if you're working with a larger model, instead of sending everything, you would want to reduce the context. This people typically do when they are working in long conversation history. They would essentially collapse it. They will essentially send it to us, summarize it with a smaller model, and then that summarized response will go to a larger model. Then generate a distilled model from a larger model. So you have a larger model, you ask it a very specific questions and answer, you get it, and you train a smaller model out of it. I'm going a little bit in hurry because I ran out of time. And then you can combine output of other modalities with larger models. So you may want the model's input to be an image, an audio. With Gemini Pro 1.5, this may not be necessary because native multi-model input is supported. But for your some use cases, you may want to do it. So let me quickly cover the future landscape of AI. So Gemini Pro got released with 1.5 million context, and what that essentially allows you to do is ingest an hour of video, 11 hours of audio, 30,000 lines of code, and 700,000 of word. And this allows you to do complex reasoning. So if you go to the YouTube channel of Google, you will see a full Apollo report was shown, and then a question was asked like image, what was the movement of this? And it was able to clearly predict this is essentially representing Neil Armstrong's first step. And in another example, from a library called 3.js, though all the sample code were ingested, that essentially took like around about 816 tokens. And then a slider of animation speed was requested. Create a slider that will control the animation speed, and the model was able to do it. So these kind of things were not possible before, and I asked you to explore some of the other things that Google has done in the space of alpha geometry and alpha code 2, because it opens new type of patterns on how to essentially build out new type of systems. So how to mix classical ML technologies with modern LLM technologies to build out results which have been never seen before. In this case, alpha geometry, almost there at like a gold medalist level in like Olympic gold medalist for mathematics. Similarly, it is more than language. So Genome, which is a DeepMind model, was created, and now it can search in a much larger space than what humans or traditional computational methods would do. So you have like access to new type of material. So you would have seen the hype about superconductors out there, right? And the next level of leap would come from machine learning, and this is like a peak in that. So the takeaways is this: it is not open source versus closed source. You basically build out a system that composes everything. Do what you can for like accurate and reliable responses, and for which composable architecture would definitely help. And be on the lookout for new ways to solve problems. And as you would have seen with tree of thought architecture. And the last one is generative AI is more than text. So that's about it. I'll take questions outside. Thank you.